Good morning, boys and girls, and welcome back. Talking more volumes of solids today, although today we'll be revolving around the y-axis. Again, both attacking the disk and washer method, I believe, all in one fail swoop today. All right, so let's give it a go. So for our first example here, we're given the equation y equals x squared, x equals 0, and y equals 4. We want the area enclosed by these functions, and again, we're going to revolve around the y-axis now. So let's again first start by sketching a picture of what's happening. Alright, so we have y equals x squared here, and the line y equals 4, and the line x equals 0 is the y-axis. So this area right in here, we are going to take and we're going to revolve this now around the y-axis. Okay, so it's going to revolve like that instead of around the x-axis like we did yesterday. And again, I think part of this is just try to visualize what's happening, what's going on, what kind of shape are we going to create. Right? In this case, it looks maybe something kind of like that. Again, going back to yesterday's discussion as well, you're going to want to ask yourself, is there a gap between what I'm revolving around? All right? So if I'm going around the y-axis, no, there's not. This is touching the whole entire time. Say it's our area is touching the whole time. If I were going to rotate this around the x-axis, then yes, there would be a gap, and so I'd want to use washer method. But in this case here, because there is no gap, we are going to use the disk method. All right? So no gap equals disk method. No gap equals disk method. All right, so that's what we're going to use right now. All right? So disk method again is A to B of the whole circle, so pi r squared. Now in this case, because we're going to wrap around the y-axis, we're going to want everything in terms of y, right? It's going to be way easier to do things in terms of y than it is in terms of x's. So our limits are going to have to be in terms of y. We're going to work on that in a second. And my variables are going to have to be all in terms of y, so we're going to want dy. When I start a problem, I frequently just attack it this way and be like, okay, what method do I want to use, disk or washer, and with what variable am I going to integrate with respect to? Dx, dy. So that kind of helps get me focused. So I'm kind of like trying to chip and chew away at my setup piece by piece. Real fast, before we get too far into this too, I want to go back to our website and maybe we can take a quick view, just once, of what this is going to look like when I go around the y-axis. Okay, here we are back here again. We have the y equals x squared graph, and now we're going to revolve it around the y-axis. So around the y-axis now instead. And you can see we get this again kind of, I don't know, satellite bowl looking thing. All right, bullet top, I don't know, kind of looks like that. But this is again what we're going to try to find the volume of. All right, so revolve around the y-axis now. Okay, again, if you try to get this mental pitch in your head, I do think it helps when you try to set things up and when things become more abstract. All right. Now we see it. All right, let's go back to the problem. All right, so we have our setup. We're using disk method, a to b pi r squared dy. But now, again, we need everything in terms of y. So my limit in terms of y, now I'm starting at 0 on the y-axis, and I'm going up to 4. So the limit for this problem, I'd go from 0 to 4. All right, pi, and again, you can just start by, I don't know, probably getting used to this now. I can put this pi on the outside. Right, we always pull it out anyway. Pi, now the radius is the function, but again, I need the function, if this y equals x squared, but I need the function in terms of y, right? Like that's going to be our radius, but I need it in terms of y, not in terms of x. So what we're going to do is we're going to come to the side here and write y equals x squared, and we're going to solve for x. So x equals the square root of y. Or technically plus or minus the square root of y, right? But because this is going to the positive side of the y-axis, this would just be x equals root y. That is the function that we are dealing with. Okay? But I need this in terms, this is what we mean by in terms of y, right? Y is now my independent variable and x is the dependent, so I want to get x by itself. All right? So pi r is root y squared dy. And now we are ahead and set up. And now this becomes relatively simple. Pi 0 to 4, root y squared is just y, dy. Antiderivative of y is pi times y squared over 2 evaluate from 0 to 4. And so I get 8 pi minus 0 pi, or 8 pi would be our solution. All right? That is the volume of that solid revolved around the y-axis. The only difference today is we're just doing things in terms of y and kind of getting used to, visualizing it this way. Okay, here we go. Next problem. Y squared equals 16 minus x squared. X equals 0, y equals 0. And again, we want to revolve this around the y-axis. This one here, a little bit trickier. We got to recognize what function we're dealing with. Y squared equals 16 minus x squared. If I add x squared to both sides, you might recognize this better. But this, what you got to be able to do is recognize formulas. Oh, that's a circle. X squared plus y squared equals r squared. All right. So let's go ahead and give us a little graph here and see what we going on. All right. So there's the piece of my, my circle, my semicircle, or my circle, bracketed by x equals 0, the y-axis, and y equals 0, the x-axis. And so again, we're going to take this and we want to revolve it. There's my radius. We're going to revolve this around the y-axis. So this will be shaped kind of like we looked at last time. All right. So again, because we're going around the y-axis and because it's touching the whole time, this is a to b pi r squared dy. We're going to do it with respect to y on the setup. Okay. And now we just got to go find our r. And again, the r is the function. R is the function, but it's in terms of y, f of y. So now I've got to go, and again, I want to solve this equation for x. So x squared equals, I'm kind of continuing off from over here, x squared equals 16 minus y squared, or x equals, again, plus or minus technically, but we're going to use the positive root. So x equals 16 minus y squared, and that's our function. So we're going to do the integral pi times the integral. We're going from 0 to 4. Again, this is x squared plus y squared equals r squared. R in this case being the radius. So the radius of the circle is 4, so that would go up to 4. The radius of our disk, because we're doing disk method, is the square root of 16 minus y squared. Dy. And you notice this happens a lot. We get it works out nicely for us. I'm going to square roots, things like that, and your arithmetic should work out nicely. If it doesn't, it means you probably made a mistake. So, excuse me. So we get pi times the integral 0 to 4 of 16 minus y squared dy. And then when I integrate that, I get pi times 16y minus y cubed over 3, evaluate from 0 to 4. And when I evaluate that, I get 128 pi over 3 is our answer. Okay, here we go. Next example. Y equals 2x squared, x equals 2, and y equals 0. All right, and again, be careful setting these things up. Really think about what's happening and what your enclosed area is going to be. Take the time to graph them. All right, y equals 2x squared is a parabola, right? X equals 2 is a vertical line over here. And y equals 0 is the x-axis. So this is the area here that I'm trying to revolve. And again, we're going to revolve this around the y-axis. Okay, I'm going to take and revolve that around the y-axis. In this case, because there's a gap, that means I have to use the washer method. And again, gap equals washer method. So the washer method is the integral from a to b of pi times big R squared minus little r squared. And again, in this case, because we're going around the y-axis, I'm going to say dy. Okay? Washer method before we had disk method. All right, so now same idea here, though. Now I need to figure out my limits, and I need to figure out my functions in terms of what they are. Okay, so to find our limits, again, we're doing it with respect to y, so again, I can always turn my head this way when we're doing it with y. And so we're starting at 0 on the y-axis, right? And I'm going to some value up here where these things intersect, right? Up here. And so to find that, I need to solve this system. And so, I've got x equals 2 and y equals 2x squared. So if I just use substitution and plug in over here, we get y equals 8. So I know that I'm going to go from 0 to 8. Those are my limits. I can bring the pi out in front, and now I just need to do the big R squared minus little r squared. Big R, again, is always the top function. So if you have your head tilted again, the top function is the line. Little r is always the bottom function or inside function. And again, so what I want to do is top minus the bottom. The big R minus the little r. So big R goes out to this vertical line, or 2. So that big R is always going to be 2. That doesn't change. So my big R is 2, so 2 squared. Little r goes to this function right here. It goes to the parabola. So I need to use that function, but again, I need to get it in terms of y. So I came over here and had y equals 2x squared, divided by 2, rooted both sides. Again, I'm only using the positive one. So that little r is root y over 2. All right, and again, then we're going to integrate with respect to y. So this is our setup to find the area of this shape. Again, it's going to be kind of like a bowl-looking shape. So when you simplify that, you get pi times the integral 0 to 8 of 4 minus y over 2 dy. I take the antiderivative, I get pi times 4y minus y squared over 4, evaluate it from 0 to 8, and then when I evaluate that, you should end up with 16 pi. And there's the volume of our shape. Okay, one more example. We're going to use the same picture, but now instead of revolving it around the y-axis, we're going to revolve it around the line x equals 2. Okay, so again, same picture as last time, y equals 2x squared, x equals 2, y equals 0. But now we're going to revolve around this line, x equals 2. Again, the way I think about this, because this is vertical like the y-axis, I'm still going to want to integrate with respect to y. Okay? If I revolve around some other horizontal line like the x-axis, I integrate with respect to x. But if I revolve around a vertical line like the y-axis, then I integrate with respect to y. All right? And now if I'm looking at this where I'm revolving this around, my shape touches the whole time. So now I'm back to a disk method problem. All right? So my setup would be, hey, a to b of pi r squared dy. And we already from the last problem talked about how my limit is going to go from 0 to 8. Again, I can bring that pi on the outside, but I need to find my radius dy. All right, so our radius is right here, right? That's that little chunk right there. So if we're tilting our head to the right, like we should when we integrate with respect to y, tilt your head this way, you will see that 2 is the top function, and the parabola is the bottom function. So we want to, again, to find this, I think the easiest way to do it is always just the top minus the bottom. So if I flip my head this way, my radius is going to be 2 minus, and again, when we rewrote this in terms of y in the last problem, it was x equals root y over 2. So 2 minus root y over 2 squared dy is going to be our setup for this problem. Okay? When you're finding that radius, again, just remember, flip your head if it's with y, or straight down if it's with x, and then it's just always top minus bottom. I found that's the easiest way for you guys to come up with this radius. All right, but now we're ready to go ahead and integrate this. Okay, and to integrate it, I would double distribute here, multiply this out, and you should get y over 2 minus 4 root y over 2 plus 4 dy. And then when you take the antiderivative of that, you should get y squared over 4 minus 8 thirds root 2 times y to the 3 halves plus 4y. Evaluate from 0 to 8. And when you evaluate that, you should get 16 over 3. Right? Again, I know I'm kind of skipping over some of this antiderivative and evaluating stuff. I'm expecting for us to be able to do that at this point. But if you got questions, come back, ask me. We definitely can go over those types of things. But that's you have it for today. Integrating with respect to y, we're revolving solids around the y-axis. All right, thanks, boys and girls. See you again real soon.